All right, we're back for day 16 of Advent of Code. Here we go. Another grid. It's a maze. 90-degree turn is the very first move. Okay. What does the lowest score reindeer could possibly get? They can turn 90 degrees, move forward one tile at a time, but never into a wall. Also rotate, increasing their score. Wow, okay. This is going to be a Dijkstra's problem. So let's get the grid. It's going to be shortest path with like a weird looking adjacency system. So let's see, find the start and find the end. They're located with S and E. Okay. First, let's just walk through the grid and find these. And then while we're at it, let's also just like clear up the grid a little. Once we have the locations, we're fine. The first thing we're going to start at, okay, it starts by facing east, I believe. Yes, starts facing east. So the directions are going to be, we need to like rewrite our adjacency list in the correct order. So we start facing east. We also need the curder. The current direction is going to be 0, and facing east is going to be 0 plus 1. And then left is going, we'll say going forwards in this list is rotating clockwise. So then this will be -1, 0, then 0, -1, and then 1, 0. And then the starting location is going to be, okay, so this is going to be our distance, and this is going to be our starting location. Our starting location is going to be this. I'm going to call this SD instead. And then what we'll do, if, let's see, if the direction that we end in does not really matter, I don't think, right? As long as it doesn't matter at the end, then I think we're fine. Yeah. So in that case, what we'll do, if CXCY is equal to EXCY, then we are done. And then the answer, I guess we'll, otherwise, we need an adjacencies function. Shoot, it does like this. Or like, it's nice to have this setup that I have. So what are our options? We can rotate either direction. So we could yield these. If we do one of these, then the cost of that is 1,000. Is that right? 1,000 for rotating? Yes, 1,000 for rotating. Or we can go in the direction that we are given, as long as it doesn't put us into a wall. dx dy, ders of cd, nx and y, cx plus dx, cy plus dy. If g and x and y is not equal to a wall, then we can yield this. That would be nx and y, and the direction doesn't change. Okay, there's our adjacencies. I think this is just fine. I had pre-written a Dijkstra's for just this moment. That's a little bit sad. We're emptying our priority queue. Ooh, that's not great. Why are we emptying it? And how are we getting to CXCYCD? CXCYCD. Yeah, how are we getting to this location? That's not right. Something is not right here. XY direction, right? How am I going from 139 to, wait, no, CXC, oh, terrible bug. Okay, let's not print this out. There's an answer, let's try it. Rank 190. Okay, sick. And then now the question is whether the tiles on one of the best paths through the maze. How many tiles are part of at least one of the best paths through the maze? Okay, so for this, what we're gonna do, so I think we no longer want to break when we're done. What we will instead do is we will finish this operation, and then we'll go through every square in the grid. And it includes the start and the end. Okay, good. And then if the idea is, if there exists a direction, ooh, this is not actually great. Because the direction matters that we entered this in. How do I want to do this? I'm actually not sure. I was going to check to see if any adjacency from this tile results in taking a step that is like the goal distance, but I don't think that works. Shoot. I guess, okay, so here's what we can do. We can create a from dictionary, which will have, sure. And then whenever we find a new node with equal or better distance, then we add it to our from. So we know that like the best way to get to this adjacency, well, cur is one of the best ways to get there. And then what we can do is we can start at the end. We can start at the end. I guess what we need to do, so this could be any possible direction. For each of the possible directions, let's do the direction, and then whatever the best distance we got to this node was, and it would be ex, ey, dr. I think that's right. Let's look at enodes at the end. Oh, that's not great. Add for set objects. This is a default dict that adds sets. What? Oopsies. Okay, enodes. Yeah, wait, all of these are, no, these are not all equal. Only this direction is the best direction to get there from, right? Because that was our answer. So actually, the only best, so what we're gonna do is we're gonna start from, good nodes, and then what we'll do, okay, so 1 exey was the direction. Let's do exey 1, I think, and then while pop the last, and then let's do it this way instead. Then what we'll do is everything in the from of sum. My names are getting worse. We're going to add it to the stack, or if other not in gnodes, add other, stack.append other, and then we're done. I think it's the length of gnodes. 616? No. Okay. Well, let's try this example again. I guess the fact that I had to hardcode this one did not feel great. But I think it was right. So I guess for starters, oh, whoops. EXEY1. Yeah, so in EXEY was this, and then DIRS of 1 was this. That's the direction we were going into. Yeah. Okay, this makes sense. We were going up. Oh, did I get these right? No, I think if I got that right, it would still be fine. If I mixed up my clockwise and counterclockwise, that didn't actually end up mattering. Shoot, I'd like to try the sample input. I'm just worried about this hard-coded one. So I guess we'll do that again. Distance of EXEY dr, and this should be printed with dr. And then we can try sample input. Okay, so the best one was still direction 1 here, and it says 57, so interesting. It actually has fewer. I'm realizing one thing that I did wrong is I am including the direction in the tile, but that would cause me to overestimate, not underestimate. Tiles are part of at least one of the best paths through the maze. I guess we can print what my thing looks like. So I'm actually going to do whoa. Whoops. Ooh. No, let's go back to what we had before. And then what we'll do is yeah, so now I think it's only 45, which is a little weird. Let's print out the grid. What am I not including here? This looks, it's not the same one, right? Second example, there are 2 examples here. Do they both finish in the same way? They both finish in the same way, so I don't need to worry about that, I think. Okay, so what am I, oh, the second example was 64. Oh, that was my bug, Oh, shoot, we fixed my bug. It was the other thing, I was overestimating, 501. Rank 86. Okay, I still got some points. Whew. Oh man, I didn't realize that there were 2 example inputs there. So I assumed that I still had I assumed they still had some bug that I had to find when really I had fixed it, and it was just this problem where I was counting up the number of, not the number of unique tiles that are on an optimal path, but the number of unique states. And a state is a tile and a direction. Oh man, okay, cool. So let's see how close I was off of anything, I guess. Yeah, okay, so a lot of things started coming in at the 10 to 12 minute mark. So I definitely could have finished pretty highly on part 2, I think. Like, I think even like maybe as high as 8 minutes or something would have been possible if I had actually, if I had not written the bug that I did. I'm not really sure my first submission was, but I suspect it was somewhere around that mark. Maybe I'm overestimating how fast I was. Yeah, it was 13 minutes. Probably not quite 8 minutes, but I'm not sure. Anyways, yeah, cool problem. Part 1, definitely seen some very fast times here. Be a little hard to write a... Well, to be fair, I did have a Dijkstra's algorithm pre-written, so that made things go pretty fast for me. But yeah, I guess I'll explain the question now. So this is a type of shortest path problem. We're given a grid and we're roughly asked what the shortest path to the grid is, with the catch being that it's not just like a normal grid where we can move in any direction, and that is like distance 1. actually we have a direction that we're facing, and we can move in that direction for like cost 1, or we can rotate 90 degrees for cost 1,000. And that's basically the whole catch to the problem. And it just says like, find the shortest path through this grid, and what is the shortest path. This is a pretty classic example of Dijkstra's algorithm. Dijkstra's algorithm is used to find shortest paths on a graph shortest paths on a weighted graph with non-negative weights. And yeah, and basically we just do that. One note here. So technically, like the graph here is a little bit more abstract than just this grid, mostly because of this extra bit of state, which is the direction that we're currently facing in. So while normally you could represent this grid implicitly as a graph, with your state being like all these empty tiles would be like nodes in the graph, and you'd have adjacencies between nodes, between empty spaces, between nodes that are empty spaces that are adjacent to each other. In this case, what you actually do is your nodes are represented by your x coordinate, your y coordinate, and your direction, and you only have an adjacency. So the adjacencies for this are there's three, either 2 or 3, and the adjacencies are either we can go in this direction, so that's x plus dx, y plus dy, where dx and dy are like the dir, and keep moving this direction, or you can like change directions. So that would be, these would be your adjacencies. So it boils down to like something very similar. We're again like we're representing this graph implicitly. We're not explicitly computing a bunch of nodes or anything, but it's like easy to compute your adjacencies on the fly, so you can just sort of do that. Yeah, this is like a pretty common advent of code style question, I think. Yeah, and I'm not going to go through like explaining what Dijkstra's actually does. Just know that it you keep like a priority queue and append things to, or push things onto your priority queue or heap in the order that you find them, or sort of. And you're basically kind of trying to keep track of the minimum distance to every node. Yeah, and then that is basically part 1. You just sort of do Dijkstra's. So I had a pre-written Dijkstra's, which made this pretty fast. The setup I had for this was like pretty minimal. It was just the core logic of Dijkstra's, which is as long as your priority queue is not empty, pop something from it, check to see if it's like if it's your goal state, in which case you're done. Otherwise, like go through all the adjacencies, and then if you're finding that this adjacency is like the best way to get to this new state, then update your distances to that state and push it onto the heap and repeat. This is like the classic Dijkstra's loop. So the only thing I had to fill in order to get this to work was I had to fill in the starting state, and I had to fill in the adjacencies function. And I wrote the adjacencies function here as a Python generator just because that's a little bit handy. It's nice to just be able to write it like this. But yeah. I didn't fully say this, but the reason it's 2 or 3 adjacencies is because this is not always valid. It's possible that you would go forwards into a wall, so this would not be valid. But yeah, and that's part 1. Part 2 is now it says count up the number of tiles that are part of at least one of the best paths to the grid, from the start to the end. So basically, there could be multiple best paths. In part 1, we only found the first one, which doesn't really matter. All the best paths will have the same distance. But now we care about all of them. And the way to do this classically is you keep track of, well, I guess there's a couple ways. If it were like the typical grid thing, where we didn't have to worry about this direction constraint, then what we would do is, what I was thinking about doing at least, was for each cell, ask what your distance from this cell to the, it's actually not quite right, is it? Yeah, never mind. The idea I had in mind wouldn't have actually worked there. the thing I ended up actually doing, which does work, is for each tile, for each state, you keep track of the best way to reach that state. So like in this process, we have this loop where we're checking to see like, is this new route to some node the new best route to that node? And if it is the new best route to that node, then we want to like update our distances. If we know that we found the new best route to this node, then we know that oh shoot, did I write a bug in here? I'm surprised that I didn't write. This feels like I wrote a bug in here. Okay, I think this actually should be that. Does this change my answer? It doesn't change my answer. I'm not sure why this worked. Oh, I think I got lucky. Not that lucky. I think this is fine for all inputs, but it's a little ill-formed what I did. I'll explain that in a minute. First, let me finish going through the actual approach. But yeah, so you keep track of the best way to get to every node, and that's this like what this from dictionary is doing. Whenever we find a new best path to a node, we know that like so we're finding the new best path to this adjacency, and we know that we can get there by going from cur. And the idea is that this is like sort of a back lookup table. We can start at the end and then go backwards to traverse our entire path backwards. And because this is a set, so if we find another path that is equal distance, then we also add that as a possible thing to go backwards to. And this lets us recover all possible paths. So that's what I'm doing here, is I'm just like, actually I'm doing a DFS backwards through this, is the way that I technically have this set up. So when we look at all the possible best ways to reach this node, we add them all to a stack, and then we pop from the back of the stack and then add those things, and that it's like a recursive thing, except we're not actually doing it recursively, we're doing it with an explicit stack data structure, but it has like the same effect here. Yeah, so now let me mention briefly the thing that I thought was a bug. If you find a new best path to some node, then you actually want to clear away what you previously thought was the best path for that node. So like if you make it from A to B with cost 10, right now I'm thinking in like an abstract graph sense, and then later you find a route from, or maybe you do this, and then you also find a path of length 1 from A to C. And then you look at C and you find a path of length 3 from C to B. Well, right now, like, so previously our from would be empty, right? After this, our from would be, the best way to get to B is from A, and the best way to get to C is also from A. And at this point, we now have found a new best path to C, or new best path to B, with like total distance 4, right? So really this should be just C. But I think the bug that is in my code is I always add to this set, I never replace it. So I actually would have done this, and this is incorrect. If you were looking at the optimal route to B, you would incorrectly conclude that the edge A to B is one of the best paths, which is not true. And that was the bug that was in my code. The reason it was not a problem is because of the actual structure of this graph. We're not dealing with an arbitrary graph where this is possible. The graph we're dealing with is such that whenever we encounter a node in Dijkstra's for the first time, that will be the best route. And that is not always true in Dijkstra's because of this example I gave here. It's possible to like later find a shortcut. But in this case, it's not possible because there's no, like the only edges are weight 1000 or 1, and weight 1000 doesn't actually take us to like a node that we would ever want to visit again if it's not on the optimal path. I'm not sure that was completely clear, but it's kind of hard to like make completely clear, so I think I'll just leave it at that. And if it really doesn't make sense, maybe people will shout at me in the comments and I'll try and explain more. But yeah, that is day 16 of Advent of Code. Yeah, I'm pretty happy to get some points today. It's obviously not like nearly as good as yesterday, but like getting some consistent points day over day is going to be like what ends up mattering a lot for climbing the leaderboard. And I'm still on the global leaderboard, and I should be on the global leaderboard for a while, hopefully. But yeah, cool. All I have for what was today? 16. Yeah. See you tomorrow.